Problem 29, I'm going to show you how to derive a formula which you will subsequently use in other problems. That formula is to figure out uh, velocities of objects after an elastic collision. You do not have to perform those manipulations in the subsequent problems, but you do need to understand it, so do take time to understand this. And obviously you're not going to be required to do it for the test, as in to derive the formula for the test, because it's algebra, not physics. And I'm going to actually put it on the sheet of formulas for you when you're doing the test. All right, so problem 29, we have an elastic collision. So it's stated right here, which will obviously never happen in real life, because we have two cars colliding, one of them, and they're real cars. So we have a van which was at rest in the beginning, and a 715-kilogram car traveling with 225. By the way, that's a plus, not one, in the Word document for homework. And unfortunately, I missed that. It has a plus 225, and in your file it's 1, but it's a strange looking one. Anyway, so the initial velocity of the car is 225, and they give you a plus to say that it's forward, to the right, whatever. After the collision, since it's elastic, they do not stick together. If they stuck together, it would have been an easy problem for baby physics. So we need to figure out the final velocity of the car and the van. So it's a collision, therefore I know that my momentum is conserved, and it's elastic collision, therefore I know that my kinetic energy is conserved. Initial momentum and kinetic energy for the van was 0 because it was at rest. So, conservation of momentum. This is my initial momentum for the entire system, because there's only one car moving, hence the 0 right here. I can just disregard and altogether. Momentum final is right here. It's two cars moving, and you can kind of predict, maybe, hopefully, that since the van is so much more massive and it's moving obviously forward from real life, you can imagine what's going on. It's going to move forward, and since this guy is about half the mass of the van, it's going to bounce backwards. So you can expect the final velocity for the car to be negative, which you will see. But anyway, so right now what I have is one equation. These two are numbers, so they are known. But then I have one variable and another variable. Two variables with one equation you cannot solve. So in order to be able to figure out both velocities, I need to bring up another equation, and that would be conservation of kinetic energy. Again, this right here is the initial kinetic energy for just one car, and that's my final kinetic energy. Both objects are going to be moving, and the energy is conserved because it is elastic. Here is where physics ends. That's it. After this, it's just algebra, so it's going to take a few manipulations to figure out how to get rid of all these contraptions and come up with a formula that will allow us to figure out the final velocity of the car. So in order to do that, we're going to do a few tricks. So the first thing, I'm going to multiply by 2, get rid of 2 here. So that's what my conservation of kinetic energy turned into. Got rid of 2's. Then what I'm going to see is I have mass of the car, and mass of the van. So what I'm going to do, I'm going to divide by mass of the car. So I'm going to have mass of the car goes, and here I have mass of the car going in the denominator under mass of the van. So this is what my conservation of kinetic energy will look like after I just got rid of 2 and divided by mass of the car. Now what I'm going to do, I'm going to rearrange this and put this part on the left with a minus, and just rewrite this as velocity final for the car equals velocity initial for the car minus mv over mc, and that's v final for the van. Now I'm still stuck with 2 variables. I don't know what this is, and I do not know what this is. So what I'm going to do, I'm going to get rid of velocity for the van. And in order to do that, I'm going to go back to my conservation of momentum, got rid of 0, so that's initial momentum of the system, that's final momentum of the system. And I need to substitute for velocity final of the van. And so what I'm going to do is like moving this over here with a minus, then I have both velocities multiplied by the mass of the car. So I'm putting it in front of the parentheses. And then to figure out just the velocity, I'm going to divide by mass of the van, and this is what I end up with. So velocity final of the van, mass of the car over mass of the van, and the difference between initial velocity of the car and final velocity of the car. So what I'm going to do after that, I'm going to take this right here and put it in here. So if you need to, go through all this one more time, see step by step. If you're good with this, I'm going to look again, I'm going to look at this equation right here and put this, which I got from conservation of momentum, instead of the final for the van. So here it goes. Okay, so again, this part is the way it was. Then I have the ratio of masses, which was intact. We kept it. And then instead of V final of the van, I'm plugging in this formula right here. So I have the ratio of the mass flipped, squared, and then square of the difference of velocities. And then since this is squared, I can take the square out and take these masses out. And so what I end up with is this. So my ratio of masses just flipped. And what I also did is I took this and put it in on the other side of the this right here. I put it on the other side of the equation sign, so therefore it became minus. And then what I'm going to do is I'm going to look at, this is the difference of squares. And as you remember, the difference of squares is the difference times the sum. And then since, if you look into the brackets, it's the velocities of the car in both cases. So I can basically take this out and this out, and I will end up with this, right? Okay, so take a breath, go back, look through this. If every step makes sense, we just substituted, and then foiled, unfoiled, whatever you want to call it. Used the old formulas from algebra. What I'm going to do after this, in order to get rid of this ratio of masses, I'm just going to multiply everything by mass of the van and also distribute this right part. So again, I'm multiplying everything by mass of the van, hence it appears here and disappears on the right. And I also distributed this. Now what I'm going to do is rearrange this so I can have velocity of the car, initial and final, on different sides. So if you look over here, I have velocity of the car final here with a plus, and velocity of the car final here but with a minus. So I'm going to put it on the other side of the equation with a plus, hence I ended up with this. And then this right here is my initial velocity of the car. I'm going to put it on the other side again with a minus. So I rearranged these guys. So now I have final velocity of the car, final velocity of the car, and then initial velocity of the car and initial velocity of the car. And I have the sum of masses on the left and the subtraction, or the difference of masses, on the right. And what is interesting here, this obviously is a positive number, but this will be a negative number because your van is so much more massive. And remember, I told you that most likely the car is going to bounce back because the car is not as massive as the van. If it was the other way around, if the van ran into the car, then obviously it would just plow forward and the car would be pushed forward very fast. So right now, since I do know this initial velocity of the car and know both masses, I'm just going to divide the right side by the sum of masses. And so again, as I said before, you can use this formula from now on, and I am putting it on the formula sheet for you. So we have that formula, and I can figure out the velocity of the car. Oops, sorry. So there we go. Using this formula, so 715 was the mass of the car, 1055 was the mass of the van. The difference over the addition, 225 was initial velocity of the car, so I end up with negative because the car bounces back. And then this came from the conservation of momentum, and so since I'm subtracting the final velocity of the car, and the final velocity of the car is negative, it ends up to be a positive number, and so the van is going forward, but much slower. Because remember, the car itself, when it just bumped into it, was going 225. So it gives some of its momentum to the van, and the van is so much more massive. So if I take 715 times 225, which was my initial momentum, and 1055 times 182, which is the final momentum of the van, indeed this final momentum of the van is greater than initial momentum of the car. And they were both to the right. This guy is going right, and that guy is going right. So since this one, the final, is greater than initial, then obviously I will have to have my final momentum of the car directed to the left. Hence your negative velocity right here. So again, this formula, you can use it in the next questions where you have elastic collision again.